Mm-hmm. All right, so it seems that we are having some sound issues, so bear with us for just a moment. We're trying to get control of sound to Mark. Mm-hmm.
Okay, testing.
Yep, we've got you, Mark.
Okay, we're back. Sorry about that. I don't know what happened to the sound. It just cut out, and that was the end of it.
Quite all right.
All right,
So
I'm ready to go.
okay, I'll kick this back over to you, and
All right, thanks.
on you're ready.
Good morning, everyone. I always enjoy doing these when there's a live audience, but I enjoy them much more when I'm in person. So webinars are never easy, but we'll make the best of it, and I think we can provide some value here. I didn't hear all of Nathan's introduction, but usually they gush about how much experience a person has and all of that. And I want to start out by saying that someone like myself, is no different than anyone else who's taken a keen interest in a particular facet of transportation engineering and has become specialized. When you spend full time at something, you're going to get good at it, even if you're not the brightest person in the room. And so that's kind of my personal introduction. I guess it's by experience and focus that I come to have the recognition of being relied upon for this expertise. We work in about 10 states regularly. I have 12 staff, 8 engineers whose only focus is modern roundabouts. And so we have developed a bit of a pedigree for this over the years. And we even have some history in Alaska with a project in Juneau that Leif Auerston assisted a local consultant on some years ago. So we come by some of our experience by traveling long distances and have enjoyed that very much over the years. So I want to do the first session on site selection with the, I guess, the purpose, a couple of different purposes in mind. And one of them is to look at the various conditions that you may or may not approve of a site being appropriate for a roundabout. So by the time we're finished, you're going to see a number of examples of roundabouts, and I know there are many up in your part of the world. But I want to try to ignite your imagination and interest in looking at roundabouts, a little more broadly, not just, in bigger, more complex situations, but also the mini roundabout, something which we've taken more of an interest in lately because of the cost cutting and responsibility we have for infrastructure. The common barriers that agencies face, I maybe try to get a bit of a dialogue going near the end of the session where we talk about that. And then the middle of it essentially is a roundabout screening study. And I want to bring to bear on some of your experience and maybe do an exchange of knowledge on what we're finding as emerging practice and best practice for preparing intersection control studies. The kind that compare alternative types of control and are both transparent and traceable, and in all their content, the public, whoever your audience is, can read these studies and find the justification to advance whatever control solution you choose. So that's kind of the outline of our approach. And I wanted to start out, for those of you who perhaps don't have much roundabout experience but may have driven one, to kind of wonder what some of the features are. We'll just do a very quick review of these geometric design elements and some of the operating characteristics. So bear with me if you've seen this many times. The principle of roundabouts being yield control. In some countries, I wouldn't take this for granted. We happen to have the driving culture where people adhere to regulatory traffic controls. But if you go to Beijing, it's pretty much first in. In other countries, in developing countries, they don't adhere to the same regulatory controls. So a device or a type of control like roundabouts only has a future if there's a cooperative among drivers. If there's a healthy amount of enforcement, education, and cooperation, then devices like this can really flourish and provide benefits to society. So examples are countries like England and the UK, where the cooperative among drivers is very strong, and the education and capability of drivers is very high. Roundabouts perform exceedingly well. They have one of the lowest crash records of any developed country. They lower their fatals, they lower their injury crashes, and they also have some of the most efficient infrastructure for the amount of pavement on the ground. And so it's not by any coincidence, but it's a deliberate thing that if you can integrate your driving education with good design, you'll achieve all the benefits of roundabouts. And I'll say a bit more about that. In fact, the challenge we're facing in North America is one of driver adaptability. And through this series of sessions, I'm going to talk a lot about design, but in one of the sessions when we go into public outreach and implementation of roundabouts, I want to emphasize that the adaptability of the driver is something we've underestimated. And so what we're seeing is some multi-lane crash frequencies and histories that are developing sort of in a negative way, that we're starting to see some intersections converted to multi-lane roundabouts with slightly higher property damage crash histories than certainly the prediction models would suggest. And to most people's surprise, we're not getting all the benefits of roundabouts at that level. So there may be a large education need that we have to deal with, but not today. We'll first talk a bit about roundabout feasibility. So how do roundabouts operate? Well, through deflected entry paths. The geometry helps to slow the vehicles so that when they arrive at the give-way point, as the British refer to it, the give-way point or the yield line as we commonly call it, that the speeds of entering and circulating traffic are relatively equal, within 5 to 10 miles per hour. That helps to motivate the entering driver to yield to circulating traffic. Very important for roundabouts. And that in itself is a strong suggestion that geometry plays a very big role in how roundabouts operate. So that yielding before entering. The counterclockwise flow, we all understand in the UK it's clockwise flow for left-hand drive, but over here, we interchange roundabout layouts and we just put the deflection on the other side from what the British apply. So they tend to have less delay than traffic signals. At least the studies and some of the early results of the last 10 years of feedback from roundabouts in operation are showing us that they're more efficient and they reduce stops, delays, and improve air quality. So there's our counterclockwise flow. This roundabout, and I'll try and give you a commentary on these. This one is it's near Hartford, Connecticut. The DOT had involvement in it. It was a county road project, shoehorned into some very tight development and access constraints. I'm sure you've seen sites like this. 5-leg intersection, very difficult to signalize. It met signal warrants, and they had to take some property, but you can see access wasn't severely impacted. So I love looking at roundabout photos. We have a lot of that in this module, and for the next 11 hours or so of these sessions, we're going to do a lot of visual. So other roundabout features: the circulatory roadway, whether it's single lane or multi-lane, whether it's striped or unstriped, and we can talk a bit about the striping issues and crash frequencies associated with it. The splitter islands that divide opposing streams of traffic, and assist with the deflection characteristics of the geometry. The exit paths and the natural exit paths of roundabouts, I rather like flatter and not so curvilinear exits, and I think they're justified because if it's a capacity device, you want to flush the traffic out of the circle. You don't want to impede it as it exits. And that, of course, depends on the quality of entry design and how slow you can get them to enter, whether or not the exit speeds are too high for pedestrians or just adequate. So there's a lot of kind of not too hot, not too cold, just right in terms of design of roundabouts. Very important that we examine context. Entries like this two-lane entry in the diagram, two approaches have a kind of a painted gore between the lanes, and one approach does not. So that suggests that there's a different classification of roadway and possibly different vehicles using two approaches as compared to the other two. So this roundabout is in southwest Wisconsin. It's on a rural high-speed roadway where there were fatal and injury crashes, and it solved both problems. And clearly lots of capacity for future traffic growth. Central Island, these days they're being mounted, although there's no safety research correlation between crash incidents and the height of the Central Island. It's intuitive for designers to want to block sight across the circle. Then the truck apron, which is probably about a 12-year-old invention. When we began to stripe roundabouts, we had to add truck aprons because lane discipline demanded that we provide additional over-tracking area for the trucks. Otherwise, we had sideswipe issues. So back around 2002, the first truck aprons began to appear on multi-lane roundabouts. That deflection characteristic is key to the operating condition. From the straight line path, it's a visual deflection, it's a physical deflection, so the driver slows as they enter. But it doesn't demand or take so much efficiency away from the intersection operation that it's poor in comparison to other types of control. Roundabouts are generally preferred at rural locations where signals can result in high-speed angle crashes. So it's a safety countermeasure. Anyone who does safety audits, roundabouts are now in your toolbox. Any location with a high crash history where you have signal warrants, or in some cases you don't have signal warrants, you may have a safety warrant, or you have some high side street delay that doesn't meet signal warrants, and a roundabout's the ideal solution. Obviously at congested intersections, and we have enough proof where roundabouts are reducing congestion very well, where there's a high proportion of left turns, where you would otherwise put in a double left turn, or you have protected phasing demands at a traffic signal that can't be served because of other demands of timing at the intersection. Roundabouts are suitable in those conditions. And of course, intersections with unusual geometry, and I'll show you a number of examples. The transition between high-speed and low-speed urban and rural environments using a roundabout as a form of a speed brake is a very attractive solution for those conditions. Short of enforcement, I call it sustainable safety. It's kind of self-enforcing by the nature of the geometry and the speed reduction that it achieves, that you don't have to put enforcement out in speed change areas and speed zone reductions. Where property costs are high, signals are usually preferred. The roundabout does take a larger bite at the intersection, the footprint, the corner clearances. Also in platoon traffic corridors where signal coordination, either one-way or two-way coordination, is achievable, and a roundabout would interrupt that. That would not be an ideal location for a roundabout. Some of the sight distance issues that can occur for roundabouts on profiles with crests where sight lines are limited, a roundabout might be suitable. But we still have to adhere to stopping sight criteria. That's very important for roundabouts to be able to see the point of entry, that visual clue that allows the driver to determine speed, path, and direction is a critical element. Visually impaired pedestrians are expected. The U.S. Access Board deems a single-lane roundabout to be an accessible intersection with the proper crosswalk treatments. That's a debatable issue, and I'll show you an example near the end of our slide set where we went to a municipality and a roundabout was proposed, but we had some visually impaired and wheelchair constituents in that community that opposed the roundabout, and the signal was preserved or rebuilt and preserved. So some interesting comments can be made about the U.S. Access Board and those issues. Where side street traffic is low and the safety is not a problem and semi-actuated signals can be used, that's often a better solution than a roundabout. So there aren't many situations where putting a signal in place would improve safety as compared to a roundabout. But if it isn't a safety problem today, then sometimes actuated control is the better solution. And we see this instance or example come up with development driveways, access, Walmart, actuated, semi-actuated control that only trips during peak hours or heavy shopping periods and is otherwise in a green for the main street is sometimes a more efficient way, particularly if it's in progression on a signalized corridor. That may be the best solution. So some of the benefit considerations is safety. That's the one that sells it. If you're trying to convince the public that a roundabout is a good solution for a location, and they are coming back and saying, we don't like roundabouts, they're confusing, they're hard to drive, it's good to empathize with them and agree with them. But the real change occurs when people equate the change that they require as drivers, they equate it with safety benefit. When you can tell them that, we understand that this is not going to be easy to learn how to drive, but it could save your life. People are willing to change if they equate it with a benefit to them. So it's important to continue to tout the benefits of roundabouts in safety. Operationally, it's a peak hour, it's an everyday situation, reduction of delay, air quality improvements, and so on. The benefits that come from roundabouts, both aesthetic and in consumption of fuel and so on, are also becoming evident. We're not so strong in the research on that side of things. We're pretty good on the safety benefit research as a design community and operational benefits, but environmental, we still could use some more studies. So those folks at the university, this is great stuff for graduate thesis and projects. Just get into the environmental benefits of roundabouts. So what are we trying to resolve? This is a photo I took on my way to lunch one day. You just happen upon this signalized intersection that everyone frequents that's, in working in our part of the world, and sure enough there's an angled collision and the fireman is, trying to disable the airbags, and this is a common sight. When we see a crash in an intersection, it's a common sight to see this kind of damage where they'll hit poles and deflect or spin. And the forces that occur, at high speeds with closing speeds that are double the approach speeds in the range of 50 to 60 miles per hour, that's when we see the severe injuries. Roundabouts have low speeds where vehicles cross paths, making them ideal. And the national research is telling us that we're reducing injuries with roundabouts between 50 and 80%. I would encourage any state DOT attendees to try to find and publish as often as you can the safety benefits being generated by the roundabouts in your area. Wisconsin missed that opportunity, and through some of the resistance that developed over the first 100 or so roundabouts, by the time they were close to number 200, they were actually meeting more resistance than they had when they started. And that's because they weren't publicizing the safety benefits. Really key to advancing your program. Other avoidable collisions, again, even at low to moderate speed intersections, this is an infrequent sight, thank goodness, but it's a common problem where we get high angle closing speeds, and these kinds of collisions are avoidable at roundabouts. Someone joked one time, where's the helicopter going to land, in the roundabout to, and how are we going to extricate the victims and keep traffic moving? And those kind of collisions just don't occur. The city of Carmel, Indiana, has reduced its fire services budget because they don't need all that equipment to extricate victims. After 70 roundabouts on their city system, they're finding they're having to attend to wrecks with this kind of intervention less often. So that's really encouraging to see that kind of result. So what do the statistics tell us? That the conversion of two-way stops, all crashes down by in the 40s, close to 90% fatal in injuries, and the two-lane roundabouts, I would say it's in the range of 50 to 70% for injury, fatal, crash reduction. And in the property damage side, some of the two-laners are generating actually an increase in crashes, and I welcome anyone to ask me about that. I was part of the University of Wisconsin investigation on some of the crash reduction in operations of roundabouts. Why are they safer? It's intuitive. If the left diagram shows you all the conflict points at a standard four-leg intersection with the highest conflict severities in the red dots, and then on the right-hand side you have no red dots, no high conflict, high severity conflicts, then it stands to reason that the roundabout should be a safer device. And all the statistics are showing us that, and yet drivers don't feel that comfortable with them. And we'll try and attend to that in the next couple of weeks of sessions. So the congestion relief, stops, delays, and idling is self-evident. You can come up to a roundabout 24/7, and instead of an actuated signal, you get to go when there's a gap, and sometimes you don't even have to stop or yield at the entry. You just reduce speed and pass through comfortably. So on to site selection. I want to show you a number of locations where I think roundabouts were an excellent solution to, again, spark your imagination as to the kind of things that are possible and the decisions that agencies have been making to use roundabouts either as a congestion countermeasure or to improve safety or to reduce crashes. So this one over in Albuquerque at Central Avenue and 8th, you can see kind of a, if you see my cursor, but this sort of free flow, likely a higher capacity, but a somewhat complex intersection condition with this left turn crossing and at unusual angles in unusual places. I don't know what the safety record is for this intersection, but I dare say it was probably efficient but not so safe. And these days in urban areas, we really like to bring pedestrians into the picture with bicyclists. And a design like this pushed the pendulum or swung the balance of the design very heavily in favor of the pedestrian and bicycle movements with low speed. It's obviously low volume capacity, and yet without signals, it's operating very efficiently in off-peak periods. So the shift is taking place, and communities are finding solutions like this very attractive to install roundabouts. That one that I showed you earlier, that rural high-speed approaches, divided roadways, they use the medians to elicit the driver's speed reduction response, the visibility of the central island, the placement of landscaping are all strategic in the development of the human factors of getting the driver to attend to the intersection and the speed control required to make a safe movement and crossing movement. So there's no longer signal heads in places like this, so the driver doesn't have anything more than the visual clues, and that puts a high demand on the design. There's a speed break from an interchange area down into a village area where posted speeds are reduced. This was an intersection that was otherwise warranted for signals, and within weeks of starting construction of the signals, they abandoned that option and went with the roundabout, and that was about 2002, and it carries upwards of about 18,000 vehicles per day. So it's a high-capacity single-lane roundabout that's providing an excellent speed control. Down in Clearwater, Florida, there's the beachfront communities with a lot of the commercial and hotel uses, and this is a separation of land use between a more residential area and the built-up commercial areas. So the residents are very pleased with the fact that it kind of creates an impediment for traffic to speed through and into their neighborhood. I really like these because they show the creativity that designers are bringing in transit. So a transit pull-out or lay-by is on the outside of the roundabout, and the use of contrasting pavements with overrunnable areas leaves the travel way intact and provides a nice pull-out for the bus, on some institutional or in some cases a university campus property. So keep those in mind. One of the most celebrated corridors for roundabouts was the conversion of Avon Road, where I-70 passes through, a pair of teardrop roundabouts at the top, and then coming down to Route 6, you have, backing up, you have two roundabouts in the center of town that replace closely spaced signalized intersections. And since these were done in 1997, there's been maybe $500 million of redevelopment and new development in these areas down to the creek area. Beaver Creek is just behind here. Former President Gerald Ford had a winter or summer residence up in that area. So these are very attractive tourist communities. And They were an excellent test of roundabouts in the early days because there weren't many in North America, and these had an excellent safety record, and they had instant congestion relief. So they really were the poster children of roundabouts. This one and the ones in Vail kind of ignited the roundabout revolution. Federal highways took note, and so it was the first roundabout corridor. Other roundabout corridors that have been done since then recognize that it's the intersections of the nodes, not the links, where the bottlenecks occur. And we all know that as traffic analysts, that we're not trying to solve link congestion as much as intersection congestion. And so the focus should be on the intersection rather than widening roads. And Leif Auerston termed the phrase wide nodes, narrow roads. And you know, the cost savings that are achievable with that wide nodes, narrow roads concept really makes it possible for communities to advance roadway improvements without the added mid-block widening costs. So there's more space. The footprint at the intersection, again, is always slightly higher. Our arterial corridor, another, again, a good example was in Golden, Colorado, where 4 traffic signals were replaced with roundabouts as sort of the bookends of the development area, with a 2x2 or 2 lanes in and out, and 2 lanes in and out on these, and then single lane by 2 lane lane configurations in the mid-block. Organizing and collecting up access. The results was instant reduction in crashes, improvement in efficiencies, increase in tax base. So papers have been published on this corridor on the commercial benefits of roundabouts. Unusual geometry, 6 legs. St. George, Utah, milepost 4. If you drive west of Las Vegas and you go up into Utah, you only go about 4 or 5 miles, and then you encounter this interchange. It has 6 legs. This is a giant Walmart. A bypass lane was added about 2 years ago for the benefit of the Walmart patrons, about 500 right turns an hour in the peak period. This little teardrop was opened up to full movements, and it was enlarged because there's a Flying J truck stop here. So these were built around 2002 and then rehabilitated or improved and upgraded for capacity in 2009. Interior to some major developments, like Sparks, Nevada, you have this 5-leg roundabout with anchors of large retail commercial. There's actually going to be a casino and a theater added onto this development. We were asked to review this roundabout and see if there needed to be any additional improvements. It has the capacity for 3-lane entries in its footprint, and we recommended that they not expand it until the traffic impact indicates that it's necessary. Rather than take the development permit and expand the roundabout, we said because of the concern for pedestrian safety, we want to find the balance between mobility and users, alternative or vulnerable road users. Very important in this context not to overkill the capacity at the cost of pedestrian and bicycle safety. And so I was brought in to kind of mediate or moderate the discussion between the developer and the city, and my recommendation was don't expand this until you have the traffic impact that suggests you need it. And they put monies aside in case it's necessary. Corridors of roundabouts, very tight, skewed interchange. You have to square up the legs, but you have to analyze these as a series. And there's a 2-step analysis method I'm going to describe in the second last session when we talk about software and analyzing roundabout capacities. This one happens to be in northeast Wisconsin, where there's an interchange package of 14 interchanges comprised of 44 roundabouts constructed over a 5-year period. So it's probably the world's largest collection of roundabouts constructed at one time. And all of the roundabouts have 2- and 3-lane entries. Some of them require a combination of oversized, overweight vehicles to pass through, and in this case of this one, they pass through the middle of the roundabout. I don't have the finished photo yet, but it was opened a couple of years ago. And we'll talk about oversized, overweight vehicles in design in one of the future sessions. Another poster child of interchanges at roundabouts was the Vail, Colorado. Notice there's a bridge with a river crossing underneath the edge of this roundabout. The undercrossing of I-70 was not widened, and the roundabouts were retrofitted with access without severe access loss. So this is a really win-win type of solution. Vail did 2 interchanges, and at the time these were built, the queues on I-70 at the off-ramps that were just stop control diamonds, the queues were in the range of a mile back from the ramp terminal. So high-speed traffic on I-70 passing the outside lane which was dead stop for the mile approaching the interchange. You can imagine under snow-covered roads how safe that would be. So this really put a stake in the ground that said roundabouts are great for interchanges and development wins in the end. So ramp terminals, the benefits at interchanges, some things that we didn't quite count on. We knew there'd be some shorter queues without signals, but because ramp flow is not platooned and not conducive to cycling, the random ramp traffic allows for smoother merging behavior onto the freeway. So interchanges where we would have expected ramp metering, the roundabout discharge pattern is random and doesn't collect and platoon traffic down the ramp, and so we don't need ramp metering. It's certainly not as early as we might in some cases if we would have added signals. That was an added bonus that we hadn't quite counted on. Cases like this, it may be a little bit different than what I just described because this is a complex series of roundabouts with 2- and 3-lane entries and bypass lanes. It's in Brighton, Michigan, which is kind of down near the Detroit area. The cost savings of not widening this bridge for the sake of this probably 1 million square feet of commercial, and the permit that was extracted from the developer paid for this improvement and the roundabout on this side of the interchange. And so big savings in bridge costs translated into improvements in the ramp terminals so that you wouldn't have to have back-to-back left turns and you could integrate these 2 intersections. But having said that, this is complex. The signing is complex, the wayfinding is complex, and this was an ambitious undertaking. It wasn't that well received initially. Michigan did not have a strong signing skill level for roundabouts. They tried to adapt what they knew, and it was met with some resistance. And someone even went out of their way to conceive a board game. And the idea was to roll the dice and try not to get lost in the roundabouts. And that was actually in the Chicago Tribune. There was an article published about that. So it did receive quite a bit of ridicule. But when you're solving big congestion problems, ambitious things like this should be on the table. One option they considered was a 6-leg roundabout tying the ramps and the frontage road in with one large circle. That was recommended against. This was thought to be, in some ways, a simpler solution. Can you imagine? I really like this one because I call it the dueling pharmacies. It's over in Kensington, New York, which is near Buffalo. Walgreens on one side, CVS on the other side, and neither one will give parking. And so you have to find a roundabout solution that's going to fit, or any type of solution for that matter. And the contiguous pair of roundabouts is ideal for that because it preserves the skews of the approach roadways, and this is also an expandable into a 2-laner. You can see the cutaways, potential for 2-lane roundabouts in these approaches, and this could easily become a 2-laner. You can see even the width of pavement is setting up for 2 lanes. So it's undersized slightly in the initial, so it opens with easier, safer operation, but is expandable in the future. So some real shining examples. This one is probably the highest volume roundabout in North America. It carries about 5,500 vehicles per hour. That's not without congestion, though. Some of the approaches, this one in particular, gets about, well, maybe 1,000 feet of queue here in the PM peak hour with 3-lane entries. This one as well in the PM gets a 1/4 mile. And it's sort of a tidal flow mechanism. If you're interested in watching this roundabout, write this down. Roundaboutresources.org is a website that we put together with a web camera. And maybe near the end of the session, I'll try and pull the web camera up and see if we can display it. There's a high-mast light pole in this quadrant, and we put a web camera on top of it. It's been there about 7 years, and you can watch the roundabout during peak periods. And it's impressive to see the operations of this intersection. Signals would have been very difficult to operate without more congestion. There's obviously constraints for water course and development, and so it was a retrofit into some tight space with even some severe vertical grades and rock cuts and things in here. Unusual geometry, this happens to be the district office for one of the Wisconsin DOT offices, and so they, the staff in the design section would sit and watch this roundabout, and before the roundabout was built, it was a signal-controlled intersection with long queues, and school buses especially, and around the 3 o'clock let-out times, release times, they had a lot of congestion, and that's all vaporized since it was open. And the safety record has been pretty good. Complex but not aesthetic, we try to go for aesthetics if we can. It's the added bonus. And down in Coral Gables, Florida, they achieved very good retrofit. A lot more green than pavement, and certainly more than what was there before. So even tight with bridges and overpasses. Some great examples. When we hit about 50 schools, and I was monitoring this database of school locations where roundabouts had been placed, and you had contact names and information from the school superintendents and the board and the parents and the police and the local agencies, and everything was coming out positive. So after about 50 sites were recorded and noted, we kind of gave up on the inventory, and at last count someone said there was about 100 roundabouts of schools, middle schools, high schools, all showing great promise for congestion relief, but improving intersections to the extent that where this might not have been accessible for pedestrians previously because of the high speed of traffic, the slow speed has allowed pedestrians to come into these areas. So the parent drop-off demand has been reduced in some of these school locations. So a real benefit to everyone concerned in terms of safety and accessibility. We're starting to see this. There's only 3 sites in North America. The one in the lower left is in Utah by the University of Utah. It's a complex system in terms of train control. Fortunately, the trains are short and fairly low speed. This one on the top left is France. The one in the lower right is Australia. Whether you use gates or simply signal control, I think for North America we're probably into the mode of using gates. We're going to be challenged to not have gates at these roundabouts. So, Bill Baranowski, who's fairly well known in our roundabout circles, pun intended, Bill has been kind of a champion of roundabouts with LRT and signals. So down in Arizona where they have the LRT, they're proposing a roundabout over in Mesa, just southeast of the city. Some of you might recognize this. I've never visited it. Leif Auerston showed me the drawings some years ago. I think we were working on some of the signage plans, and this looks like everything's just freshly opened and operating over in Juneau. But as I say, I haven't driven it. I don't know exactly what it replaced, but just judging by the bridge cross section and the approaches with narrow, bridges being preserved, that this would have been cost savings not to have to add turn lanes and extend them. And I'm certain that the safety benefits have been borne out compared to what might have been there in the past. Right-of-way constraints. I wanted to mention mini roundabouts because we're seeing more examples of mini roundabouts popping up. And Federal Highways is doing a study where they'll publish the results of some pilot studies of roundabout installations. And this is one of them where in a rather challenging context of higher speed approaches, roundabouts have been implemented. And this one, pretty severe retrofit, a very low cost, $70,000 to install, mostly paint, laid down a central island, some buttons. Again, non-frost climates in Georgia, you can afford to get away with some of these things. But they're going to formalize the curbs because what they did was reduce severe congestion at an all-way stop. And they did it so effectively with reasonable safety performance that it's kind of proven to us that even in moderate speed conditions that a mini roundabout or a traversable central island roundabout, MIDI if you want to call it, is a very effective solution, very cost effective. So we're starting to see more of that. Here's a county near Detroit, again, real cost constrained, all these all-way stop intersections, some of them warranted for signals, lots of them with long delays and long queues. We're working on mini roundabouts for a couple of intersections. And to have $1 million intersection improvement cost every time you turn around, whether it's signals or roundabouts, it just makes it impossible to keep up with the demand as development moves away from some of these urban areas. So they have to find creative ways. So the mini roundabout in this site over in Maryland, very compact retrofit to existing conditions with even utilities being upheld. The curb bump outs to improve speed control as a retrofit, again, not interrupting drainage through the edge here, but just creating a bit of a chicane or a speed control through some of the physical curb locations. And the central island is fully traversable, so there's not a lot of benefit on deflection from that, but the narrowing of the approach helps. So on to intersection control evaluation, which is sort of the heart of this session. But maybe before I do, Nathan, let me stop and break for a minute and catch my breath and see if there are any questions. And if you want to moderate that, let's maybe have a quick discussion about what we've seen so far.
Sure thing. Does anyone have any questions? If you want to, I can unmute you if you'd like. Just raise your hand using the attendee dialog box. I guess while we're waiting, Mark, I did have a question. So back a few slides ago, you were showing some arterial corridor photos, and one of which had some left turn pockets in between the roundabouts. It was the one that had the two laners at the very outer extent. Yeah, that guy right there. So there's a number of left turn pockets, it looks like.
Yes.
So what's kind of the benefit of that versus just forcing all the vehicles into each of the roundabouts to make a U-turn and then a right turn into each of the businesses?
Well, it's more expedient on the basis that these were existing developments with a two-way left turn lane down the middle of the corridor.
Okay.
So as a retrofit to stop up and close all the driveways would have been a real, you would have needed a lot of political will to weather that storm.
Mm-hmm.
So the compromise was to kind of focus on some of the larger generators and give them direct access or uphold direct access, and some of the minor generators to encourage them to make the U-turns. And you can see, so some of the driveways in the vicinity, you know, some of these minor driveways here for this fast food restaurant, they're trapped in with right in, right out and channelizations to make the movements, and they can come out and make a U-turn on the median or go to the roundabout and make the U-turn. If this was an initial development or a new corridor, it's rare to see this much commercial development occur at one time, but an agency could draw up an access management plan that would conceive of a fully divided roadway with roundabouts as bookends providing U-turns at the intersection. And if that access management plan was approved or by the agency or whether it's a council or a commission or Department of Transportation and published as such, then the landowners would know they'd either have to work with reciprocal access between uses that abut the intersection, or they would have to put up with the divided roadway concept. So where we see examples of corridors in, say, Arizona, where development occurs rapidly and in a large, in a big way, they'll start out with a divided roadway and put roundabouts at the main intersections, and then have development come out to the side streets, or have right-in, right-outs along the frontage. So this was a very comprehensive package that was triggered by, I think, one of the land uses in the corridor was redeveloping. It might be the anchor in the back here was redeveloping, and so they extracted through their development permit, some of the funding, and the rest of it came, whether county, city, and state. It is a state road, so there was, I imagine, a lot of cost sharing. But terrific. They did the speed studies, they did the travel time and delay studies. It was one of the most studied roundabout corridors, and it came out shining on all with all considerations. Reduced travel time, improved safety, improved taxes for the agency, and access didn't have to suffer. If someone wants to write in a chat question or a comment, Nathan.
Yeah, I'm looking. I don't see anything yet. It seems like everyone's content.
All right. Well, I hope my quiet voice isn't putting you to sleep. So we'll keep things moving. I sense we're going to have a bit of time to be flexible enough near the end that we'll be able to recycle and go back and look at some of these options. And if someone has questions about a specific project, they'll say, well, like you just asked, we can go back and look at some of these. Whether we design them or not, we try to maintain a history of a lot of these projects that we may have had involvement in or are aware of. Whether they're unique or there's something about them we'd like to record and keep information. I find it quite useful to monitor these because we need to recycle this knowledge. So let's move into something a little heavier and a little less eye candy, and that's the intersection evaluation. And we call them ICE reports, or intersection control evaluation. Let me just make sure I'm in the right, I'm in the right place here. So what are agencies doing and what's emerging as best practice? And this information I'm sharing with you, I do want to hear feedback from local agencies that are in the various sessions that we're holding here, because I want to hear what you're doing. That's one of the reasons I wanted to do this with the university, was just to find out who's doing what and what ground you're breaking and how it's working out for you. So I'm going to share with you what I believe to be emerging practice. It's probably state-of-the-art. If Federal Highways is involved, it's likely some of the newer material, and they work in the background. In this case, I'm going to point to Caltrans as one of the emerging, sort of a latecomer, but one of the emerging leading states in terms of the quality of these studies and how they're conducted. A lot of it has been going on in the background, but Caltrans has collected it up into a nice format, and we'll walk through that in a little while here. So why are they implementing intersection control evaluation policies? And it's for a number of reasons. And one of them is, as I started, I think mentioned, to produce a transparent and traceable decision process. There's nothing worse than going to the public and proposing something that you can't provide a defense in terms of the investment, the benefits, the cost versus the benefits. It's just not intuitive that roundabouts are the right solution, and it shouldn't be intuitive that signals are a good solution all the time either, although it's the knee-jerk reaction for many agencies still. So we're finding the burden of proof is very necessary when it comes to roundabouts. So we've had to work harder at getting our project justification. So if we do want to promote a roundabout, we have a good solid reason and basis to do so. So emphasis of context is key, and outcomes. So outcomes should tie to the problem. We can't, if we don't understand the context and we don't understand the problem that we're dealing with, whether it's crashes or congestion, then we really don't know what kind of roundabout we need to design or what the most appropriate traffic control solution is going to be. So sustainability and the avoidance of the historical reliance on traffic signal control and warrants as a method puts us in a bit of a challenging area with roundabouts, because we don't have a roundabout warrant in place yet. We tend to argue that if a signal is warranted at an intersection, it's likely that a roundabout's an appropriate alternative, and so an investigation should be undertaken. Promoting the mainstream consideration of innovative access strategies, and now we have the DDI in the toolbox, J-turns, echelons, super streets, Michigan lefts. There's just a number of these creative intersection congestion relief solutions that are on the surface now. If anyone was had a chance to go to Utah last summer, in July this year, they had an excellent forum. One of my staff went down to, they had roundabouts, but it was very heavy on the DDI. Well, I think 5 or 6 presentations. And if you go to the Teach America, all one word, teachamerica.com website, they likely have all the videos. I know they have all the videos because we've shown them to our staff. They have all the videos of all the presentations, and you'll see slide sets like this with the talking head in the background, and they explain, case studies from all over the U.S., the emergence of some of the best practice of DDIs, and putting them in context with roundabouts and other single-point urban interchanges and different types of solutions. So there's just been a surge in improvement of intersection control and innovative intersections and interchanges. it comes at a very good time. Roundabouts perhaps was the seed for that, and so it's had to take some hits and bruises for having pioneered some of this innovative intersection stuff that we're working on. So what is the emerging best practice? And in a nutshell, it's a two-step study process. Often studies of roundabouts move quickly to step 2. But I want to emphasize the benefits of step 1 for the sake of agencies that, it sorts out cost issues with doing the studies themselves, the cost of the study. It sorts out, the practical feasibility of solutions, and it separates impractical options from practical options. So there's sort of a high-level, review or screening that goes on where you identify all the possible options at a very cursory level without an exhaustive geometric design exercise or analysis investigation. And the aim is to see whether the solutions are practically feasible, whether it's roundabout signal, interchange, stop control, always stop, whether there are fatal flaws in any of those options. One example is a shining one is signals aren't warranted. So, and the point being that there is no value in taking an unwarranted signal forward as a solution and comparing it to other feasible and viable and practical solutions, when in the end you say, well, we wouldn't put the signal in anyway because it's not warranted. And I've honestly read probably dozens of studies where impractical and infeasible options are being exhaustively analyzed, in excruciating detail with performance measures, cost, and safety predictions for measures that are actually not even warranted or justified. So, work that we've done with agencies, we've moved to this model. Federal Highways, when they consulted with Caltrans and retained some outside help, they moved to this model. And the attachments that I've asked Nathan to send to you all contains two packages. One is the Caltrans bulletin outlining the process, and the second one is something that I wrote that is maybe a little softer version of it for an agency such as a city or a county. And so this is again aimed at the goal is to produce a traceable, transparent decision-making process. And in order to do so, we have some engineering and science to apply, but we have to do it in such a way that we don't carry forward options that are really impractical. So there's a note here, see email for draft guidelines. I'll open those up in a few minutes, and we'll take a glance through those and maybe stop for some discussion about that. So what are our options? As you all know, stop control, and we see this frequently where the always stop is used as a safety countermeasure, and for rural intersections. Some states have policies not to do it, but they still, whether it's through political intervention or simply to respond to a crash problem that they can't address immediately, they'll install an always stop. Very low cost solution, but it may not provide the longevity and the capacity improvement that you need to couple with the safety improvement. Of course, the one that we know with signal warrants, we're all too familiar with the signal control, and I haven't added the other ones but the roundabout. So we're going to kind of keep this discussion fairly simple. I'm not going to go into DDIs and interchanges today, single point urban or even J-turns to displace lefts. We're just going to focus on these three as sort of options for intersection control. So we're probably talking, trunk highways, at-grade intersections, county, city, state. So in the step one process of practical scoping and screening of alternatives, you need a concept level understanding of the intersection control strategies. Concept level being very cursory in terms of footprint, in terms of CAD effort, in terms of analysis, and you're examining that solution to see whether it meets the transportation purpose and need consistent with system performance criteria, whether it's safety and level of service or a combination of that, and of course cost as a reality, meeting the financial constraints of the project. So a simple example is you want to put a roundabout in an intersection, but it takes an historic building on the corner to place the roundabout. So the roundabout may be feasible in terms of system performance, but financially and environmentally, it's an impractical solution. So it does not get carried forward to any further screening or evaluation. That helps the public process, and it helps the agency, and it's a deliberate approach to solving the problem, not carrying so many solutions forward that may be impractical. The evaluation it should be done in a team effort. I think of these this pre-screening step one is kind of a panel approach where you have folks from different skill sets, planning, operations, design, and possibly community coming together to do that high-level review. I've done safety audits in a charrette type of VE study where you start on a Monday and have the report done on a Friday, and you do all the field work and consultation in between. And throughout the week, you have people coming and going that have different input on the project. So the project sponsor and someone with traffic background, folks that understand the cost and the safety benefits of the improvements, and of course spiced with good engineering judgment, and sometimes a committee. And I've used this term Innovative Intersections Committee deliberately because we in the roundabout community that do this full time have encountered a challenge where agencies have developed a roundabout team or a focus on roundabouts to the extent that they've developed a committee on roundabouts. I honestly have to tell you, it's like painting a target on something that you want people to criticize. Because of the emergence of innovative intersections, my advice to agencies is if you're going to do a committee approach, lump roundabouts in with everything else that's innovative. Don't separate it out. Don't make it so unique. It's in the toolbox for traffic safety and congestion relief, and let's count it among the alternatives. So at a committee level, you have people from different backgrounds and input from an agency, and you're not just looking at roundabouts, but you're examining other types of intersections. And what this gives you is the ability to create standards, policy, and it's uniform. It's not just a standard or a policy that relates to roundabouts that isn't integrated and uniform with other types of control. So as you move and roll these things forward and out to project level and programming, that you're doing things in a kind of a coordinated fashion with not just roundabouts, but all types of innovative intersections. And there's a preamble in the introduction of the policy where I talk about that. And maybe while I'm at it, I'll pull this document up. You can see this, Nathan?
Yeah, we can see that.
Okay. So this just happened to be this particular client. Back earlier in the year, they asked me if I would help them develop some screening criteria and a basis for conducting feasibility studies. Fort Worth, Texas has a very ambitious program. I've already built a dozen roundabouts in less than 2 years. From planning to construction in 6 months for a series of 4 roundabouts, just really intensely going after some of the benefits of roundabouts and corridors. They came back and said, well, we really need something to help us screen and identify sites and screen out sites that we shouldn't be putting roundabouts in, because with that much enthusiasm, there's a chance they're going to put one where it doesn't belong. And that's like putting an unwarranted signal. It's going to develop resentment. So we talk about a coalition of technical specialists from the Transportation Public Works Division whose experience provide foundation for policy and practice development. Anything new like this, requires a concentration of effort. Roundabouts don't just pop into your toolbox. They have to be brought in a coordinated fashion and from people who have experience with new traffic control devices and all that comes with it. So there's a mission for the committee and the coalition and who should staff it. One of the first tasks is to develop policies to support the use and implementation of roundabouts. In a subsequent session from today, we're going to talk about implementation. And again, I would like to hear from agencies who have had some experience, both good and bad, as to how they've implemented roundabouts and everything from administration of policy down to funding and practice development, staff level, politicians, what kind of experiences are you having? And this is, the key for the public. Consistent, predictable operations, improve safety performance, reduce congestion. And whatever solution will give us that is what we should be building. So through the policy, we go through some of the considerations of when you should use roundabouts, signal warrants, and these are very important policy level considerations that you decide, what's going to constitute the need. And so when you have a signal warranted, you're going to look at a roundabout. If a collision problem exists and you have your top 5% at the state level, a roundabout is in the toolbox. I'm pretty sure that's the case for Alaska, as it is for many states now. Safe schools, corridors, and access management plans, and congestion mitigation, air quality improvements. This in italics is a statement that comes from a number of agencies, and I've kind of blended it. Again, we'll talk a bit more about that in implementation, but it's essentially a policy that states that when the city has a problem with an intersection that involves safety, operations, and cost, it's going to consider a roundabout as an option. It doesn't commit to their use, but requires a test of the practical feasibility of the roundabout. So moving down into the intersection control studies element. So we've sort of covered the preamble of why you need a policy, what is the foundation for setting up intersection control studies in terms of a committee, in terms of standards and policies. And then this is the ICE report or intersection control study guidelines. And I plagiarized some of this from the Caltrans document, again emphasizing context. I mentioned this, the pre-selection of signals and promoting creative solutions. And it clarifies, the report study process clarifies how safety performance is considered during the evaluation, cost effectiveness, innovation, and different strategies are brought into the mix at through the initial phases, the step 1 and the step 2, and then describing the process itself, how it needs to meet the transportation purpose and need for the step 1 or the pre-screening, if you will, the financial constraints of the project. The practical evaluation, I've had this in some of the slides, as you noted earlier. Then the step 2 evaluation is, I'll move back to the slides in a minute here, but you're just covering some of these things there where we do analysis of operations, safety predictions, cost, and I should put my phone on Do Not Disturb here. And estimation of costs and safety benefits. Some of the qualitative things like environmental and pedestrian and bicyclists and speed control and so on. And I'll go back to the slides and show you that. Okay, so back here. So the comparison of typical right-of-way needs. This is again a practical consideration. If the roundabout takes an exhaustive footprint from the corners and there are buildings and property and it makes it prohibitively expensive, then you may want to remove the roundabout as an option. This was an illustration prepared for a project in New York State about 10 years ago, and this visualization was very powerful in working with the local businesses and residents as to how the roundabout would fit the character of their neighborhood, how it might improve safety and reduce congestion for an always stop controlled intersection. So the visualization might be a step 2 or stage 2 element where, or even at the design stage before you go to the public, you produce something like that. So I want to break the step 2 comparison of options into 2 categories, quantitative and qualitative. Quantitative being the things that we can numerically articulate, things like the prediction of vehicle delay and queuing under horizon year and existing year, things like the collision history that we can document to identify the problem and how successful any type of control would be to eliminate a crash problem. The economic analysis components are part of the quantifying of costs. Not all agencies want to use an economic analysis. There are some pitfalls in doing it. I'd like to I'd like to mention and discuss those. Economic analysis, maybe moving to that part of it. The life cycle analysis typically focuses on a design year, and we have a discount factor. So we calculate the net present value of the cost of 20 years of maintenance, the electricity, the crashes over the life of the project has a present value associated with it, and we'll compare options in terms of cost based on crash reduction potential, even delay costs, or cost of time in delay. You can even factor and quantify environmental benefits and look at the the present value of the cost of fuel and so on. The pitfall is that if you look at a particular design year, you may overlook the benefits of roundabouts on a permanent basis. And I have an example that's coming up where I highlight the fact that by using a particular design year, say 20 years from the date of construction, you miss the fact that at a policy level, the roundabout may be preferred over the traffic signal. And what results is we get trapped in the use of numbers to justify our decision making. So it's important to recognize that these studies are useful, but they shouldn't be the only tool in deciding on what control gets placed. So by way of an example, so an agency like Urbana, Illinois, says that generally they will use roundabouts in place of traffic signals to reduce congestion and crashes. If they start embarking on life cycle cost analysis that accounts for crash reduction and it accounts for construction cost, and let's suppose that the construction cost was very high for the roundabout, and although it had good potential to reduce crashes, the construction cost in a life cycle analysis still does not bear out the roundabout option, and the signal becomes preferred. The pitfall of that is that at a 20-year life cycle, that may be a justified solution to install the traffic signal. However, if you look out another 10 years or 15 years, no agency would conceive of, say, just replacing the signal with a roundabout at year 20. You would think that the signal would be in place permanently. And so the study is kind of pointing to a short-term view of things when your policy might suggest that over the long term, the roundabout is still the better solution. How do we reconcile that? We have a study that tells us that we shouldn't be installing a roundabout, and then we get a policy that says that roundabouts are generally preferred. This is where engineering judgment comes in, and where policies come in. Societal investments for infrastructure is a factor where we just make a decision that pedestrian and vehicle safety is more important over the long term, and we're going to suffer some short-term excess costs. I don't have an easy answer for that, but I'm going to show you a case study, and perhaps you can reason it out for the people that you serve. And as part of the quantification of process in this step 2 detailed comparison of options, we'll take the design layout and we'll perform some checks on it. So in some cases you'll have roundabouts are the only solution, and there may be 4 different roundabout options possible in that comparison. And so one roundabout may perform better than another. And I hope to show you an example of that if we have time. So comparing operational performance, we'll talk a little bit about some of the models later on in these sessions. But we want to quantify delay and queuing, and using Synchro, in some cases VISIM, for a system level review for signals, predictions of delay and queuing for the roundabout, and these are the popular software packages. I used to be a big advocate of Rodel, but Arcady was sort of the parent of Rodel, and it's been upheld and maintained very well, so we like Arcady. Just an aside, near the end of our sessions, I think in 2 weeks, we have a session where we're going to do some of the software. And if you're still with us, I'm going to send out a link where you can download a demonstration copy of the software that's a full version of it, that you will have access and use of it for up to 3 weeks. And we usually do that so that you can play with the software either before, during, and after our session, and get a good, good exposure to its usefulness and And I'll give examples of the kind of things we've been doing with the software for roundabout capacity prediction. So we'll compare the two options, signals and roundabouts and stop control, under peak conditions and sometimes off-peak conditions if appropriate. And if we have a system of roundabouts or a system of signals or combinations of roundabouts and signals, we'll use simulation. And that's quite attractive for the public meeting process too, that you bring that to bear on the public process. Now, this is an important area too, is comparing safety performance. In North America, we've got some well-developed safety prediction models. They're still not as well developed as the UK, who happen to have more roundabouts, who happen to have been researching them in greater depth than we have. So they have more history on their crash prediction models. So they're able to get down to not just intersection-specific comparisons, but arm or leg of the intersection-specific comparisons. So they can look at safety performance functions for a particular approach to an intersection, whereas we're still dealing with intersection-level estimation of safety performance. So I'll talk a bit about those models in a minute here, but what we're trying to do is compare safety performance of alternative controls. And so we need to estimate, what's the existing condition, and we're comparing the safety performance prediction to the existing condition for the 2 or 3 types of control. And in the after conversion, we've got some good studies that show roundabouts are reducing crashes, as they started out saying, somewhere in the 50 to 70, 80% range. And so we have collision modification factors coming from either the Highway Safety Manual or the Federal Highways Clearinghouse. They're published through the websites, and you can also get them in NCHRP Report 572, roundabouts in the United States. That was the watershed study that led to the Roundabout Guide published in 2010. It's entitled Report 672, which is an informational report on roundabouts. And the 672 report replaced the year 2000 report from Federal Highways, which kind of started the roundabout revolution, really U.S.-wide, for standards and guidelines for roundabouts. A lot of agencies have adopted that. So the report 672, its foundation was report 572, the research on roundabouts in the United States. They did speed studies, capacity studies, pedestrian-related studies in terms of safety. They looked at costs, and they developed the guidelines that we use now out of that 572 report. So getting on with the comparison, so we're talking about delay comparison, safety comparison, and then cost comparison. Those 3 quantitative criteria, I refer to those as the sniff test. If you're going to a council or a commission to promote the use of a roundabout over some other type of control, you lose your audience on details that are not as significant as safety, capacity, and cost. So if you're bringing in lots of little quantitative and qualitative detail, they tend to be suspicious of that kind of detail, because our models and research isn't so robust and rigorous in the minor details. We tend to like to stick to the high-level stuff. So when a politician reads your study, they do the sniff test and said, yeah, that seems to make sense in terms of cost and safety benefits and congestion relief. I'll buy that solution. And the public are the same. They're much more discerning than they used to be, and they read these reports and they're better educated. So we try to stick to the higher level quantitative measures like safety, capacity, and cost. So in the economic evaluation, right away is a big factor. Construction cost is obviously a big factor. The addition of turn lanes with signals can add to the signal cost, whereas the roundabout has the wide node footprint with the narrow roads on approaches. I mentioned that life cycle cost comparison is beneficial, but use it with caution. Don't rely so heavily on the report that you overlook good policy making and decision making and engineering judgment. The maintenance costs for roundabouts. Initially, when we were doing comparison studies between roundabouts and signals and stop control, that we would argue that the maintenance cost of signals was an added cost, that we didn't have an equal cost on the roundabout side. But that's not true. What we're finding is that roundabouts and signals maintenance cost is about the same, and that's because the pavement marking, signage, and lighting costs associated with roundabouts is quite high. So where are we going with this? Combining these things, you're looking at different control types at this second stage where you've screened out options that are not practical and feasible in terms of project goals. These options are, so in this case the signal would be a warranted solution, the roundabout's warranted, and the always stop is probably the existing condition. So the crash costs by confidence level, and we like to publish these because the safety models are still not so well developed that we can say, you know, the crash cost is always going to be this value. They cover a range, and they vary according to the types of intersections, the speed of crashes, whether the injury is low or high. We've kind of factored, if you look at these numbers more closely, you'll see that the crash costs by signal are higher in the mean than they are for the roundabout. And I wonder if anyone can tell me why. Does anyone want to chat me in a little line there and just say, oh, I know why that's higher, if it isn't obvious? This is your chance to participate. So why would the signal cost be for injuries or all crash types? Why would the crash costs be higher for signals than for roundabouts? Well, the simple answer is the severity of injuries is higher for signals than it is for roundabouts. So we don't have KA type crashes, you know, fatals and incapacitating injury type crashes for roundabouts. We have slightly incapacitating and non-incapacitating injuries with roundabouts and property damage. So, you know, our average crash costs at roundabouts is going to be lower. It stands to reason. So we'll take information like that, and these values are published. If you're going to do life cycle type cost analysis, you need a good source of injury and property damage type crashes, and we usually subdivide these values into property damage versus injury, and this table has done that. So a mean injury crash cost was separated out from property damage, and in this case, the signalized intersection, we're actually publishing the injury costs and the roundabout injury costs. The signal maintenance, this is an older study. We should have penalized the roundabout for some maintenance costs for lighting and pavement marking. And so this, I think the study that I used this slide from is probably 7 or 8 years old. And we've learned since then that roundabouts do have a maintenance cost associated with them. So the two-way stop control, signal, roundabout, not a huge difference in costs and benefits in terms of the construction costs, slightly higher roundabout, better on injuries, you know, maintenance. But you could tip these values depending on whether you use upper or lower limits and come out with roughly about the same costs, you know, between the two types of control. And that creates a bit of a dilemma. Then how do you decide? And it's sometimes the policy direction on the use of roundabouts that becomes the determining factor. So moving from a quantitative analysis to a qualitative analysis, the second step of that screening step 1, step 2 detailed comparison of options, the qualitative measures, some of which you could quantify, but we dare not for to avoid criticism, because the environmental benefits, the vehicle noise, fuel consumption emissions are not so well researched that we have absolutely reliable values to report for comparing different options between signals, roundabouts. So we tend to deal with these qualitatively. And in many cases, the roundabout, you know, in the studies we do have, shows not just how much better, but the fact that it is better. It's got reduced emissions, it has reduced fuel consumption. So we tend to say qualitatively that the roundabout's likely a better solution in those cases. We have crash statistics on peds and bicycles, but we also have ADA impacts. So those need to be considered on a context basis when you're doing the comparison. Aesthetics, it's hard to argue against a roundabout when you have that much green space in the center of the intersection. Construction staging, this is a very important one at the feasibility study stage. I want to stop and highlight this one for a second because it's often overlooked. We're doing operational comparison, we're doing safety comparison, but no one does enough detail on the constructability of a roundabout in many cases to realize the impacts, during construction that need to be accounted for in the comparison of options. If you can't stage construction to preserve and keep open approach roadways and the impact of closing them is too severe, then perhaps the roundabout should not be considered. And this has sometimes been overlooked, and they've been trapped into having to build a roundabout under very difficult traffic conditions. So I want to highlight that as an important criteria when making a comparison of alternative controls. And then the benefits, some of the speed control can be quantified. Signals have a green, traffic passes through at high speeds. Roundabouts, it controls the speed according to geometry, and generally it's in the range of 20 to 30 miles per hour. Goods movement, mixed reviews on goods movement, so I wouldn't say that it's always a benefit to have a roundabout in terms of goods movement. It somewhat depends on the type of vehicles and whether they're oversized and the frequency and percent of trucks at an intersection. And those, again, are context specific. So there's creative ways that you can do your reports and make typical comparisons. Results with pie charts numerically. There's just needs to be some way to kind of quantify this comparison, and some way that is, inscrutable in terms of the public eye and other technical professionals. They can look at your report and they can reason out what you've done in terms of the benefits. We've got both qualitative and quantitative measures built into this overall evaluation, so it does have a bit of a blurring effect where you can say, well, some aspects we can quantify and other aspects we cannot, and yet we're still applying pie chart diagrams to all of these values. And so we have to be reasonable and fair and balanced in our approach, and not put so much reliance on the results that come out of these pie charts. And yet we still need a decision-making process. So it does become a challenge when you're blending both quantitative and qualitative results. This is a table that I pulled together recently where we're doing a couple of different concepts that involve, all three are in fact roundabouts, all the other options are not, and we're comparing them based on all these evaluation criteria, and some of them quantitative and some of them qualitative. So we put in sort of the cost should have been probably on the high side of this chart, where we say, cost, safety, and capacity are the three most important, and then some of these other considerations that we can't quantify so well, we still need to qualitatively argue for and against different options. And this is a rather transparent, traceable decision-making process, but when you're splitting hairs over, the size of the pie or the chart, it's sometimes difficult to apply some good science to this decision-making process, and engineering judgment and heuristics and experience are really necessary. This is an example where, the reason I like this one for alternative evaluation comparison techniques is that it applies weighting. And this is very important, that in a case where you have, where the cost of the improvements is about the same, but the safety benefits for one might be slightly, edging another one out, then you may want to consider applying a weighting criteria. Now, this is somewhat subjective, but this can align with your policies. If the importance of safety in rural areas is very high, you can argue for a higher weight on safety than on construction cost, and certainly on mobility. And then you can see how it bears out in your options, that it's a multiplicative effect on the different options. So whereas in a semi-urban or suburban example, the weighting can be different. In this case, both capacity and safety are very high. Pedestrian and cyclists are important, but sometimes the improvement isn't for their sake as much as it is for these other motivating factors. And so we sometimes downscore a little bit. Well, depending on who you ask, this one might be the most important, and then pedestrians show up at your public meeting and tell you that. So a good evaluation, you should be able to do a sensitivity analysis and vary the weights and run the analysis again and come out with generally the same answers every time. And then you're in the in the sweet spot in terms of decision making for the option that seems to be emerging from the process. So some sample intersection studies. We'll kind of wrap up with these, and then we've got to open it up for questions, because after about an hour and a half here, we've been going for that long. I want to have a break and let you have some input. So I'm going to show you these two studies, and these were done at the life cycle cost level. And so they were done with cost-benefit type analysis, not incremental cost-benefit, just a straight-up comparison of options. One was a signal, the other one was stop control, where signals were warranted. And I'll walk you through just some of the highlights of the studies, what led to the need, and some of my comments and the issues and pitfalls we ran into. So Urbana is the home of University of Illinois, a grid street pattern. So you could argue, well, they should be putting signals on these majors because they can get good coordination at half-mile spacing, quarter-mile spacing. But the city's proactive about replacing or introducing roundabouts in some of these corridors instead of signals. As they expand out to the east to this Highway 130, they're talking about extending these roadways and having roundabout-only corridors as they move out into some of these rural areas. So the need statement for this project, it was an aging traffic signal that needed to be replaced. So it wasn't high on anyone's crash history database. It wasn't in the top 10 locations that needed countermeasures. It just was the typical signal rebuild required. And the city said, well, let's explore whether the money we put towards the signal could be used and leveraged to install a roundabout, and whether that would be a more cost-effective solution. And that's a virtuous, ambitious cause. The major considerations of the type of control include vulnerable road users. So this intersection was right next to an apartment that served 6 people with disabilities, some blind and some in wheelchairs. What was at the intersection was a countdown and audible pedestrian accommodations. So it was fairly modern in the sense of the pedestrian heads, location, the feedback devices and such. It was modern in that sense, but the signal head placements were poor, and the condition of the equipment was poor. So it was time to do an upgrade. Some of those initial concerns of installing a roundabout included the ability of the roundabout geometry to manage truck traffic. So this was on a thoroughfare and needed to accommodate truck traffic, so there might be some major property acquisition to get an adequately sized circle. Fortunately, that wasn't the case, and a moderately sized truck can still fit through. Here's our intersection. Turn lanes in all directions, bike lane integration, northbound, southbound turn lanes in all directions, the bike lanes continuing through the intersection. Some commercial developments in the area. This is the apartment building in the corner. The transit stops where the pedestrians would cross the roadway and pick up the transit bus on this side and head to the east or go towards the campus westbound. The intersection was frequented by vulnerable road users. The roundabout option, rather shoehorn design, a radial design in terms of the center line being essentially up the middle of the roundabout. So slow speed exits, fairly slow entries. It does accommodate a WB62, making left turns and right turns. So it's not the full highway WB67 accommodation, but for through movements, certainly the highway vehicle can get through. Integration of some of the pedestrian and bicycle treatments with a diversion point on the south leg, wider shared use sidewalk, property impacts associated with that, crossings and re-entry points with the bikeways coming back down to pavement. So it had all the elements of a modern roundabout, adequate width for crossings. We discovered we could develop a fairly robust layout. And we'll talk a bit about costs, but essentially it met all the criteria. We could get speed control, a combination of trucks, a combination of vulnerable road users within a reasonable footprint. So those are our focus for the design. Now designs like this, so maybe stepping back, so at a conceptual design level, you sometimes wonder, well, how much effort's involved if you're going to do comparisons of alternatives in the ICE process, as we call it, intersection control evaluation. You know, you have to apply a certain amount of detail into these designs. And so when it comes to something like this where you're dealing with a retrofit and you've got some potentially severe impacts on everything from driveways to property, you've got to develop the layout in quite a bit of detail. This, I would argue, is probably a 30% level design. What would remain to take this to contract plans would be profiles and grading. But essentially the horizontal layout is in a final, you know, we're comfortable with its functionality. It meets all of the performance requirements for a modern roundabout, everything from sight distance to the vehicles and users. And so this is about the level of detail that you need to develop concepts to if you're going to do a thorough job of comparing alternatives. So the existing and future operations, about 15,000 vehicles per day through the intersection, not a heavy volume for a signalized intersection. And the signal, you know, today operates at about a level of service B. Let's look out about 15 years. Operations, we're going to see about a 3,000 vehicle increase. Still going to be level service A and B, whether it's a roundabout or a signal. And the roundabout is just a little bit more efficient during peak periods. So a comparison of delay shows that the roundabout would be an efficient and cost-effective, or at least an effective solution in terms of capacity. Reduced delay, reduced emissions. Now the crash information is interesting. So we're going to apply a life cycle cost analysis to the crash data. And the problem is that if it isn't a safety problem today, you know, it's applying a lot of rigor to what is otherwise really a non-starter. You know, with only about less than one injury crash per year, you know, at present with the signal and the future of the signal, and even if we cut that down by 50%, it's not noticeable to the public. You know, the safety benefits are not so noticeable. But I can tell you what would be noticeable to the public, and I refer back to those vulnerable road users. They like their signal, they're comfortable with the use of the pedestrian audible, and the prospect of a roundabout was not well received. And that's in spite of the fact that U.S. Access Board deems a single-lane roundabout to be an accessible intersection. So yours truly had to sit at council with these blind and folks in wheelchairs waiting to get up after me, and I had to stand up and state that a roundabout is an accessible intersection by definition. I had a hard time doing that, you know, realizing that the signal had all the accommodations and would have the same in the future modified or rehabilitated condition, and that the roundabout would require, you know, some level of intervention for pedestrians to be able to cross, even though it might be single lanes and the crossings are short. So this was a bit of a wake-up call for me about, well, 2-3 years ago, where I had to go and face the music that we've been saying it to everybody, that roundabouts are accessible to blind pedestrians and folks in wheelchairs, but that's a bit of a stretch at the best of times. Here's what keeps me focused on the roundabout as a solution. At signals, and in this one we went out and experienced this, and you all have done this. You push the button and walk, and someone tries to make a right turn on red and almost knocks you down. That hidden risk associated with signals is something that most of society discounts. We think that the signal is safer because we have this right-of-way guaranteed, seemingly guaranteed, by pushing the button, but it's not. And we prove that to ourselves by walking this intersection. And so I was able to make statements like that. The roundabout lost in the end, but for this reason and for other reasons, it didn't surface as the preferred solution. So we did the comparison of alternatives, roundabouts to signals, rebuild of the signal, roundabout in its place, and the annual injury costs were, you know, surprisingly about half, as we mentioned, 54% reduction, and quite a bit lower for the roundabout. The peak hour level of service, slightly better for the roundabout. The capital costs, significantly higher for the roundabout, you know, almost $500,000 in favor of the signal. But when you factor the capital and life cycle costs, the roundabout came out ahead. So why does the municipality decide against the roundabout? Well, it came back down to the vulnerable road users in the context of that installation. And, you know, for a city that doesn't have a lot of roundabouts, Urbana said, you know, we want our first few roundabouts to be shining examples. We don't want to put ourselves in a very difficult position, you know, for introducing roundabouts in this context. And so, and I concede that. I think if in their position, I understand their what's motivating them. So in the comparison results, the single-lane modern roundabout, it fits the right-of-way. It has narrowed lanes. It has nice short pedestrian crossings. It lowers speeds. So for lots of good reasons, the roundabout was a great solution. Superior safety performance, better efficiency, but the higher costs. And this is out of their pocket. The injury crash costs are not recovered by the agency. And so that's one of the weaknesses in life cycle cost comparisons, that unless you can bring these dollars back into the agency, the reality is that they're going to have to pull out of their pocket or a fund or a bond another $500,000 to build the roundabout just to provide that safety benefit over 20 years. And we tend to think short term, and you know, political careers are about 3 years, and spending like this seems to be excessive. So the benefit cost ratio was quite good, you know, better than 1, which at a minimum should be 1.5, almost getting to 2, with a payback or a recovery for society, not so much the agency, but society benefits by having a crash reduction recovery of the cost of improvements over about 7 years. Okay, the second and last of the 2 examples, same municipality, suburban now. So the campus of the university is over here. So we've got some higher speed, moderate speed arterials. In the area of the intersection, we have a park in the southeast quadrant. We have a church in the northeast quadrant. We have some experimental farms in the other quadrants and university property that's either vacant or has some passive use. So we're kind of in a moderate speed change area where coming into a residential and some institutional with a retirement home in the southeast quadrant, we see the need for a bit of a speed break. The intersection is always stop controlled today, and so that speed break exists in the stop control but wouldn't be evident from the signal. And there's driveways to development and residences that would be impacted by, you know, having a green indication where traffic can speed through, and you don't have a two-way left turn lane downstream of the intersection. So there's an interesting context, not unlike conditions I'm sure you've encountered elsewhere. The needs of the intersection, signals were warranted. Not a lot of collision experience. In fact, neither of these 2 intersections were in the top 25 locations identified by the city. And that should have been one of the first clues that if you're advising an agency on sites that are suitable for installation of roundabouts, try and aim for the worst problems. You say, well, why would we want to risk that? And that's because you can get the highest benefits. And all the examples that I showed in those photo slides prove the benefits of roundabouts where conditions were almost impossible to do anything else that would be either cost beneficial or reduce congestion and crashes as effectively as roundabouts. So the mantra or the code that I live by is solve your worst problems using roundabouts, because roundabouts trickle down. You solve a bad problem with roundabouts and you'll never look back. And this was, I think, the mistake that we made with Urbana, was not targeting the top 20 or 10 locations and saying, look, you've got a much more severe crash problem here. Let's go out and attack that. You know, and if a roundabout's justified, you'll get so much benefit, everybody takes note, and you look like a hero. And then you get the goodwill to do another one and another one and to continue with the program. So sites like this that weren't high on the crash history radar had signal warrants, but that's not unusual. They don't look like a good candidate for roundabouts, and as the study bore itself out, the roundabout was not the chosen solution. But let's look at the results. So I talked about the context: nearby seniors' residence, regional park, bike paths, church, pedestrian traffic at the intersection. The all-way stop works for them. They're pretty happy with that. Low pedestrian exposure and crashes. It's a speed break, so they're quite happy with that. And the public meetings, we wanted to make it evident that if they got the signal, which is what a lot of them wanted, they were going to have a green light in the conditions downstream with high speeds crossing the intersection that they didn't have before. And that would put pedestrians at risk and access of driveways more difficult. So again, in the comparison of options at the detailed level, we've already pre-screened. There are no other options besides the signal and the roundabout. So we're working down into that level 2 analysis of detailed comparison, and that requires a footprint sketch, concept diagram, if you will, for the intersection improvements associated with signals. So not a lot of change, pretty much within the existing pavement. Turn lanes already there today, 2 lanes in each direction already there today, even the 3-lane cross-section on the side street. So this retrofit's pretty cheap. You know, there's no property required. The signal can be installed quite cost effectively. The roundabout, on the other hand, big bite in terms of right-of-way, even though it's maybe passive land use. Someone has to, you know, buy that, and the university has to give it up. The alignment's shifting to avoid property takes and impacts to everything from little garden areas. And even though the speeds are low, the impact is bringing the intersection closer. The church, the signage for the university, just a number of impacts. You can see the larger footprint to create a functional 2-lane roundabout. Again, those sensitive users and large trucks and access being important considerations of the context. Again, not a high volume intersection with signals warranted, a slightly higher increase in traffic, roundabout, level service A, level service B with the signal, good efficiency improvements if roundabouts were installed instead of signals. Good delay. Here, the crash reduction, a little bit better for the roundabout. The 1.64 is the signal. This is the signal today. And so slight increase in volume at the signal means that there's going to be a slight increase in crashes. So not a decrease, but we're actually going to install signals from the stop control and have a worse crash condition in the after. Hard to justify the signal as a safety improvement. So looking at the final numbers in injury crash comparison, level of service, the roundabout looks pretty good. Capital cost, huge difference in favor of the signal. Capital costs in life cycle, slightly in favor of a roundabout, again, because the crash costs reduce. So this is the slippery slope of doing life cycle cost analyses, that if you're going to factor in injury crash reduction, it's going to offset your construction cost, but you need to have the will to carry solutions like this forward when the construction costs are significantly higher. You can see the big difference there. So they have to find another close to $1 million instead of installing the signal. In spite of the maintenance costs of signals, they're going to need that kind of money to get the project going. So the big property footprint, the property impacts, the short pedestrian crossings, superior safety performance, but the higher cost essentially disqualified the roundabout. Cost benefit of the roundabout, 0.3. Long recovery period. So it's tough to cost justify the roundabout, all things considered. So they went ahead and programmed the traffic signal improvements. So that brings us to the close of we've got about 15 minutes left, Nathan, and maybe while we're stacking up for questions, I'm just going to see if I can get the web camera going. So if some folks want to ask some questions about any of the content, I'll pull it back up. Or any comments about experiences. I'm interested to hear what types of studies people are using to compare intersections, and whether anyone has been doing the 2-step screening, 2nd-step detailed study.
Sure. What I'll go ahead and do is I'll just unmute everybody, and if you've got a comment or a question, just go ahead and chime in. Hopefully, we won't get too much feedback. Mark, we get a question from here at UAF. Typically, what's the length time of construction for just a small single lane modern roundabout?
Okay, it depends on the complexity of the intersection, and let's assume that you didn't have right-of-way takes, and the utility relocations were limited. We started in February and had an opening for a single-lane roundabout in September. One of the ones that I showed you, I think one of my first projects back in 2002, we did an arterial roundabout, and construction was about 14 weeks, start to finish. We did limited drainage and undergrounds. The municipality came back after and did the lighting. We had some utilities to relocate pole lines and things. The staging was a partial closure of the intersection, so we took advantage of the closure to expedite construction, and that's the kind of thing you can get away with.
We got another question from Ethan, who asks, do you have any thoughts on using roundabouts for access control on frontage roads?
Access control on frontage roads. So you're talking about a facility parallel to, say, a trunk highway with an intersection that's in close proximity to the trunk highway?
Yeah, exactly.
Is that okay? Yeah, that's where you get into very close spacing situations. If I could do this quickly, I'd jump to Google Map, because that's a common problem in the Highway 41 corridor, where some of the trunk highways that cross US 41 have parallel frontage roads, and it was determined that if they're going to have a roundabout at the intersection with the cross street that links the frontage road, they're going to have to put a roundabout at the frontage road as well. So you're talking about roundabouts in very close spacing. The space was almost impossible, so they left them in stop control but linked them up with the roundabouts, and that made it possible not to need to have signals at the frontage road, and to put the frontage road up against the roundabout that was on the arterial. They could service the traffic better than if it was signal controlled, because typically what happens is you have to bunch traffic. By nature of the signal, you're waiting for a cycle, a phase change. You've got traffic bunched up at the frontage road trying to get out onto the arterial, and they all want to turn left and right off the frontage road into a tight space. The roundabout sets up with shorter queues, and the traffic is randomly entering and discharging. So the gaps are more frequent and the queues are shorter, so it stands to reason that the frontage road close to an arterial is better served by a roundabout than a set of signals. And if you look at the Google Maps, US 41 south of Green Bay, you'll see the roundabouts in those interchange and frontage road situations with very tight spacing. In some cases, 4 roundabouts in 1,200 feet with 2- and 3-lane entries. In 2017, the Roundabout Conference is going to Green Bay, and if you get a chance to come down here, you'll be able to drive them and walk them and bike them. Let me just see if I can't get, I'm looking for a web camera.
So I went ahead and remuted everyone because there were, I was getting a little bit of feedback on this end. So if you get a question, just use the question dialog box.
Yeah, see if something comes back. Let me know if you can see this. It's going to come up streaming in a minute. This is the web camera.
Yep, we can see it.
So it's a live web stream. It's 16:52, or it's about 4. It's almost 5 p.m. This is the heavy approach in the p.m. and then these other 2 approaches in the a.m. And with 3-lane entries, this is a flared entry from 1 to 3, and it's a double spiral roundabout with single-lane exits, coupled with 2- and 3-lane entries. So there's a complex striping plan, complex overhead lane designation signs, and there's obviously a pedestrian about to cross there. You can see them coming down. We record, if anyone wants to do some capacity studies on roundabouts like this, we record this every hour for 7 days, and then the camera recorder resets. So we can extract the video files on an hourly basis, and if you are adept at counting entry flows and circulating flows and doing the kind of study that Professor Belz did with his gap and saturated roundabout entry study, this would be ideal to observe because we have saturated entries. And the saturation occurs for long enough periods to get kind of capacity response and behavior that we would expect at capacity conditions. And you see different driver behaviors, forcing gaps, accepting gaps. Some entries suffer more delay than others because of the circulating flow. The PM peak, and we're maybe just a little bit beyond it right now because this has universities and hospitals. It was probably about a half an hour ago. You would have seen more saturation on all these entries, but it carries in the range of 5,000 vehicles per hour in the PM peak. And overall, on a daily basis, it's about 55,000 vehicles per day. So there's a constant move up of traffic. Although the queue is there, it's a rolling queue. It's not the same as a signal queue. Just keeping an eye out, Nathan, for other questions.
Yeah, we're looking pretty quiet on the question front.
Okay. Yeah, that's a lot of material to cover, isn't it? I'll make the slide presentation available offline in the form of a PDF. So if folks that want to look back at the material, or I guess are you going to put it onto a website?
I am. I'm working on the details of where to host it. I guess it depends on how large each of these video files end up being. So we'll work that out, and we can work on sending the information out to everyone so that they have that. Right. Well, if it looks like there aren't any other questions, we can wrap up for today. And so those who are in attendance, I noticed one person had to duck out. We had a couple leave here, but that you'll stick with us for the rest of these. And again, a thank you to Mark for being here with us and sharing his insights and knowledge. And so Friday again, same time, same channel. Is part 2, so design principles of speed control, space for trucks, and rural designs. I don't know if you want to give a little bit more of an introduction to it, Mark.
Sure do. Yeah, just to say, I picked hot topics. I've over the last few years done a number of knowledge exchanges with DOTs, and I usually ask them, what's hot on the radar, and often the topics that are in the list for Friday and a couple of other days are the ones that come up. How do we deal with trucks? How do we deal with pedestrians? How do we look at roundabouts in a system? The kind of stuff that isn't so well developed in guidelines yet or research hasn't quite addressed. We give you sort of a practitioner's view of it, a reasoned approach to it, not always a bulletproof sound design method, but certainly one that you can feed off of and say, I'll take some of that and I'll apply that and I'll wait for more research if I'm going to develop a standard or something out of it. But we try not to profess any absolutes without absolute data. So I think that'll be a good session. I hope it's a little more interactive. Please give feedback to Nathan so that I can modify, improve, or whether it's to talk slower, talk faster, or to have more breaks. Let me know what you need. Let me know what you need, and we'll work with you.
Sure. We got one more question, Mark, and then we'll wrap up for today. But Ethan asks, where might I find some more information for application of roundabouts on rural high-speed roadways?
We have a session on rural high-speed, and I want to go into thoroughly into detail. I'm not sure I heard the first part of the question, whether a specific aspect of it?
Just where one might find more information for the application.
I'll send you a paper.
Okay.
It was done in 2005 for a Caltrans project. We did some speed study sampling of roundabouts. Hillary Eisenbrand, who's now at Federal Highways, did some good crash reduction and speed studies with rural roundabouts, and her paper was published in Seattle in the spring, and I think she's put it in a couple of circulars. So there's some good basis for some of the benefits of roundabouts and rural high-speed.
Wonderful. All right, with that, let's close it up for today, and hopefully we'll see everyone again on Friday.
Thanks for your attention.
Thank you, Mark.